So Arya, do you understand what is equilibrium constant?
I don't understand what is equilibrium constant. Very hard. Eric, do you understand what is equilibrium constant?
Yeah, in nature, everything seeks balance. Water levels out, heat spreads out, even in reactions, there is a point where forward and backward processes even out.
Oh. In chemical engineering thermodynamics, we call this equilibrium. And the number that tells us how that balance looks?
It's the equilibrium constant, which is K.
Let's imagine a sealed container with chemicals A and B reacting to form C.
We are reactant. We are going to turn into product in full speed.
Well, I'm product, but I can convert back into reactant too. That's how reversibility works.
Reversible? Let's see how about that.
At first, A and B are turning into C quickly, but over time, C starts turning back into A and B. As time passes, they go back and forth until they reach balance. Eventually, both reactions happen at the same rate. This is equilibrium, not because reactions stop, but because the system becomes balanced. The equilibrium constant K tells us what this balance looks like.
So, let's look into the maths behind it. The definition of K are given by equilibrium constant, K, is equal to exponential of negative standard Gibbs energy change of reaction over gas constant and temperature, or with its logarithm form, lane K is equal to negative standard Gibbs energy change of reaction over gas constant and temperature. So, now let us recall back what we have learned before. Standard Gibbs energy change of reaction, delta G, is equal to summation of the product between the stoichiometric coefficients and the Gibbs energy of pure species, I. Standard property changes of reaction. Standard Gibbs energy and standard heat of reaction varies with equilibrium temperature. Since standard Gibbs energy change of reaction is dependent on temperature, therefore an equation is derived out. So, by assuming standard heat of reaction is independent of T, then Van Hoff's equation appears. After rearranged, it shows an equation of linear line. The negative standard enthalpy change of reaction over gas constant will become the slope. For exothermic reaction, it is positive slope, K decreases with increasing T. For endothermic reaction, it is negative slope, K increases with increasing T.
Let's apply this to the bubble process, where nitrogen and hydrogen form ammonia, a vital fertilizer. The reaction is exothermic, so engineers lower the temperature to increase K and push more ammonia to form.
But too low, the reaction becomes slow. So we find a balance, suit for exact thermodynamics and K to guide us. That's why understanding K is essential for reactor design, optimization, and reaction.
What it matters in chemical engineering?
In chemical engineering, knowing the equilibrium constant helps us predict product gain, design reactors, and set costs.
Whether we are making vaccines, fuels, or fertilizers, equilibrium helps us make smarter, more efficient process.
In conclusion, the equilibrium constant is more than a number.
It's a thermodynamic lens showing us how energy, entropy, and temperature shape chemical process.
In nature, in industry, and our world, everything runs toward balance.
And K helps us understand where the balance lies.
We have found balance.
And now you understand the equilibrium constant.
Thanks for watching.